Now, in processing, because sometimes, like I keep saying, let the data speak. Let the data speak. This is the reality. The data can go a long way to determine if your algorithm is going to work or it's not going to work, no matter how much you try. So sometimes pre-processing might really be needed. And you remember this generalized iterative process. This is data preparation, feature engineering, data modeling, and performance measure. We explained this yesterday. So the first kind of pre-processing you might want to do is missing data and the treatment. So what is missing data? Missing data is you have your Excel open or your file in any location. You see some columns might be having a lot of missing values. Sometimes they are rows. Sometimes rows and columns missing at random. What are the causes of missing value? Maybe somebody entering it made a mistake. Maybe that value was not available at that point in time. Why is it required to carry out missing value treatment? Because missing value can actually confuse your machine learning algorithm, because it will not be able to generalize appropriately as it should be. And what are the methods of treating missing value? So these are all very important aspects. However, if your data is very fine, the one we use today now, the data doesn't have any missing value, everything looks good, we are good to go without doing any missing value treatment. That is fine. But how do we answer all these particulars, all these questions here? So there are specific videos in our previous engagement that we have discussed them in detail, and I'll kindly refer you to that. Because of our time, we will not be able to go into detail, but you need to be aware sometimes when you are using your data and it's not cooperating or you are not getting good result, you may need to go and look at your data for possible missing value treatment. At least you are aware now. The second thing under pre-processing, there is outlier detection and treatment. What is outlier? Outlier is when you have a particular value that is not in the range of other values. It's just abnormal. I gave an example yesterday. Let's say I'm treating my student student record. It's being processed for a particular machine learning algorithm to be model to be built. And I noticed that the age of a student is 238 years. Other students are just 23, 22, 21. Why will a student be 238 years old in undergraduate program? It's impossible. Something must have gone wrong. This is called outlier. So we need to detect the outlier. So what is outlier? This is what I've just said. What is the impact of outlier? Just imagine you have your data. All the data will be arranged on the number line. This outlier will be totally far away from their colleagues, which means your machine learning algorithm has to struggle to understand this far away data. So sometimes we might need to treat outlier. And outlier is more challenging than missing value. A missing value is easier to treat. You can easily know that there's something missing. But outlier, because what is an outlier for a column? This is student age. 238 is an outlier. However, if I'm talking of the cumulative mark of student, cumulative mark, all the student might have 282, 293, 482. You know, this is cumulative of their mark for the entire program. Some of them will have, so the same 283 that is an outlier under the column age is not an outlier under cumulative grade. This is why outlier is very difficult to detect. So what is outlier in one column is not an outlier in another column. You cannot just look at your data, like you cannot just look at your file and say, oh, this is an outlier. No, you have to carry out some procedure to be able to identify an outlier. One of the simplest way to do it is what we call box plot. It's in Excel file, very simple. Put your data and draw a box plot. It will show you how those data are distributed. And then the outlier will be far away from other people. Then we can try to see. So how do we detect outlier and how do we treat outlier? It's similar to the way we treat missing value, by the way. However, like I said, it is more challenging to detect outlier than detecting the missing value. Again, for the sake of time, I will recommend us to our earlier videos where we discuss outlier detection and generally pre-processing processes. Another thing we might need to do sometimes is called normalization. A very important process sometimes, data mining or machine learning process. You want to normalize. Why do we normalize? If your data is good, nothing strange, it's okay. But sometimes you have age is between 23 to maybe maximum of 25 or 30. This is the range of the age. That's why in the beginning of your data analysis, you have to tell us the range of your data. But there's another column, like the cumulate, like maybe the total income for the company. We're analyzing a company income. And some company could be like millions, several digits. So when you're having, and the same company, how many number of staff in that company, maybe just 23 to 50 is a kind of range of value. And this one is like 10 million or even more, or billion. So when you have different columns with different range of values, then it's good for you to normalize the data. However, I do encourage people, just put your data into your platform, either Weka, Python, whatever you are using, and then run it first before you start normalization. If it works fine, that is fine. That's okay. You see, that is okay. So, but if it is not working fine, then we might need to start looking. Maybe we need to normalize. When you normalize, we have different normalization. It could be min-max normalization, Z-score normalization, or normalization by decimal scaling. In which case we can convert this 10 million to between 0 and 1. Everything should be between 0 and 1. I don't care whatever value you have here, I will convert you to between 0 and 1. That's why we just use one here. We've converted $73,000 to become 0.716. So that all the data in that data file will be of the same range of value. This is what we use normalization for. And there are different types of normalization. However, I discourage people from normalizing their targets. If you are working with regression, because if you normalize your target, after the prediction, you must return it back to before normalization. You see? Because, and the good news is if you normalize, you can always convert it back because it's a formula. You see? This is the new value. This is the original value. You can easily make this one to become the subject of formula and you can get back the old value. If you have to normalize your target. Usually I don't normalize my target, but some people like to do it. If you do it, don't forget you have to return it back to the original after you get the value you are looking for. So, and other pre-processing stages activities you might need to do, like balancing the data. If the data is not balanced, let's say you are having like a classification with 300 class A and only 20 class B. This is imbalanced data, 20 against how are we going to solve this problem? We use balancing of data or data balancing to do that. We can up it or we can down as appropriate. We can use oversampling. We call this oversampling. This means you increase the one with lower number to become 300, or undersampling. I will reduce the one with 300 to become like the lower one, 20. This is under the balancing of the system. And towards the end, before we finally call it a day, feature selection, also very important. Like I said, we won't be able to cover everything, but just let you know, there are concepts like this. Feature selection, sometimes you have features. So we need to reduce it sometimes. The total number of features, you cannot really appreciate the work because it's not able to, the more the number of features, the more the time, of course, the more the number of samples you want. So a very important terminology I'm going to explain to you is cost of dimensionality, so that at least you can take that home. This is feature selection. We started with full feature. We try to identify useful features, and we come up with these 4. Imagine, I'm developing a machine learning system for medical processing or medical diagnosis. This used to be 15 features. If I'm able to reduce it to 4, that is a very huge thing. Let's say I'm using all these features and I'm getting 95% accuracy. Can I reduce to 4 and still get 95? That would be very, very wonderful. It means it's easier for people. Imagine someone needs to use some medical model and you ask them to go and do 15 medical tests before they can use your system. That is so much costly for people and also waste of time. I try to reduce by using feature selection so that we can reduce the number of features without compromising the result. That is why we say feature selection is given a set of features. We want to find the minimum set of features that achieve maximum classification performance. It's also another optimization procedure, by the way. You said you want to use few things to achieve something that is better. That is feature selection for you. So sometimes you need to do it. Like the example we demonstrated, that data set has almost maybe around 12 or 13 features. Can we bring it down to like 5 or 6 and still get the same better accuracy or even better? Sometimes you get better result when you do feature selection, actually. Let me clarify this. Because if your data set has fewer number of samples, this is what we call cost of dimensionality. Cost of dimensionality. Cost of dimensionality is the required number of samples to achieve the same accuracy grows exponentially with the number of variables. As you increase the number of variables you have, the number of input features, the needed number of sample increases exponentially. This is the challenge. You have one feature, you are getting 95% accuracy. Good. You have two features, you have 3 features. As the number of features increases, what happens to your performance? It goes down until you go to 0. Why? Because the number of samples is fixed. Your client will send you like 375 samples. You can't increase it because you are not the owner of the data. Even if you want to increase it, the data is not available for increase. You get across to our client. It said us there was a case of a client that sent us 375 samples. We said this is, and then they have like 15 variables. This is huge. We said, okay, we need more data. They said there's no more data. When we run the experiment, we were struggling with 60% accuracy, which is very low. Then we started the idea of feature selection. We brought down the feature selections to like 5, and we were able to get like 95% accuracy. So because the features, this is cost of dimensionality. It's a serious problem in machine learning. This is only, you have only one variable here. Can you see? You have only one variable. Then you can see that you can still get 100% because there are 10 samples. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. We have 10 samples and only one feature, X. So our performance can be 100% because if the new sample is coming after training, we have this point representing blue. This one is representing blue. If any new sample fall here, we know you are blue. If any sample fall here, we know you are red. We can still do the classification because every sample is now a representative value. Now let's increase the number of features now to 2. When your feature becomes 2, X1 and X2, now we need sample to fill every slot. No slot should be empty. So which means when the samples was 1, we need 10 raised to power 1, which is 10. We got it. Only 10 features, only 10 samples. Now our feature has increased to 2. We need 10 raised to power 2, which is 100. Look at it. We only have 10. The number of samples are fixed. Our client don't have extra samples. Then what do we do? You can see here, 1, 2, 3, 4. Look at how many missing spaces. We would like to have representative values for them. This is why we said, as the number of features increases, the number of sample needed increases exponentially. When you say something is increasing exponentially, our mathematicians understand this better. It is the worst form of increase you can have because you can never be able to solve that kind of problem. Now let's increase this number of features to 3. When the number of features becomes 3, 1, 2, 3. Now we need 10 raised to power 3. That is 1,000 samples. And we are still struggling with only 10. So these 10 are struggling to understand the nature of the data. You can see all these empty spaces, they are a problem for our model. So we have to do feature selection to reduce the number of features back to 1 that can do the work for us because we don't have samples to increase. The more the number of samples, the better. But sometimes we don't have enough sample. So we need to reduce the number of samples. Now, that is cost of dimensionality, that the number of features needed will increase as we increase the number of features. And then wide feature selection, and host of others. And finally, we have discussed this. All these concepts I've described now, they all form into what we have told ourselves, the generalized machine learning model, data gathering, data preprocessing, model building, model testing, the need to refine the model validation, prediction using the model, result analysis. We have discussed this one. All these concepts we have gathered, you need to combine them together into one to have what we presently have now. And then finally, sometimes these things don't work as we want it to work. You use a single model, it doesn't work. You don't get good result. You have to use all the models you want. Sometimes the data is so complicated. In that case, you can easily switch to try to combine several models. You're trying to combine several models together so that you can be able to have a better system that might be able to do better for us, as the case may be. This is what we call ensemble machine learning method. Sometimes we need to use ensemble machine learning methods. When single model cannot solve a problem because the data is very complicated, then we go for ensemble, because ensemble has been demonstrated to have the capability that if you have a very, let's say you have 25 base classifier and they are having an error of this nature, if I am able to combine them together, each of these classifiers is having error of 0.35. What? Assume the classifiers are independent. The probability that the ensemble classifier will make a wrong prediction is going to be 0.06. It means the error rate of the ensemble will be lesser than the error of each of the classifiers. This is why when things go so wrong with our data that we don't know what to do, we go to ensemble system. And because of our time, we won't be able to look into this anymore, how I wish we could. But for the sake of it, the idea of ensemble is we want to have many models. Look at this elephant. This guy is touching this. He said it's like a big snake. This one is saying, oh, this is like a sheet. This one is saying, oh, it's like a drum. Each of them is a model. So you train a model to understand this. This one, with everybody will know what to do. They can all combine together in what they say in my local dialect. That's it. When you gather things together, you can actually be able to achieve better results. That is, in unity, there are a lot of opportunities and a lot of strength in that. And that is what we call ensemble model. You can see here, finally, look at this very unique, simple example. You have here a model that is actually, it's wrong here, it's wrong here, it's wrong here. Here, this one has 3 mistakes. This one has 3 mistakes. This one has 2 mistakes. This one has 2 mistakes. When we combine them together, can you see that we achieve 100% accuracy, by the way? This is ensemble for you. Even though each of the model we are combining, they are having mistake, but when we combine them, we didn't have any mistake anymore. Why? We combine them for this first sample. This is sample here. Is it going to rain today? Is it cloudy? This guy said, no, it's cloudy. This one says it's not cloudy. We say, okay, how many of them? Out of 5 models, 1, 2, 3, 4. 4 against 1. We choose 4. Majority carries the vote. These 2 of them are wrong. 3, majority. We get it right. So when you combine together, the mistake of some will be canceled by those that are correct. And then we get better result. This is what we call ensemble. And I recommend for us, we visit say we have more than 6 or more than 4 or 5 videos in the past where we discuss ensemble in details. However, remember, in machine learning, you start with the simple. If the simple fail, then you start going gradually to the complicated one.